Hi, welcome back. At the end of my last video, I mentioned that white dwarfs are the ultimate fate of stars roughly equivalent in size to the Sun. And in this video, I'm going to talk about what happens to stars significantly larger than that. And while doing so, I'm going to reference a unit of measurement that astronomers use called the solar mass, which is exactly as it sounds. So 2 solar masses means twice the mass of the Sun, and so on. This will allow us to talk about what the thresholds are when a star is too big, for example, to become a white dwarf, and also allow a comparison of the final mass of an object with the mass of the original star. So, for example, the white dwarf that will result at the end of the Sun's life will not weigh as much as the Sun. I mentioned how when the Sun expands into a red giant, it'll throw off its outer layers and become a planetary nebula, and so the final white dwarf will weigh significantly less. Current estimates are it will weigh a little bit more than half a solar mass. So whatever the threshold for the actual white dwarf is, the star that gives rise to it can be significantly larger than that. And it would seem that stars of a mass up to about 10 solar masses will result in a white dwarf. However, the white dwarf will not be heavier than 1.44 solar masses. That is the absolute upper limit for how heavy a white dwarf can get. It's called the Chandrasekhar limit, named after the Nobel Prize winning physicist Subrahmanyan Chandrasekhar. He, along with others, had extended the work of Fowler, who had come up with the idea of electron degeneracy as a mechanism by which white dwarfs could support themselves against gravity. And Chandrasekhar's breakthrough was realizing that there was an upper limit to that if the mass of the white dwarf was too large, its gravity would be too strong and it would collapse past that point supported by electron degeneracy. Now, this was controversial at the time. Physics at that point was dominated by Arthur Eddington, a giant of physics, second in his day only to Einstein. The problem was that at the time Chandrasekhar announced his findings, there was no known mechanism beyond electron degeneracy that seemed capable of stopping the complete gravitational collapse of the star into the already theorized black hole. And Eddington and Albert Einstein at that point loathed the idea of black holes and thought they were nonsense. Eddington remained opposed to Chandrasekhar's ideas for the rest of his life. This was one of the reasons why Chandrasekhar did not actually receive his Nobel Prize for his discoveries for over 50 years after he published his paper. There are multiple ironies here, not just are black holes real, but that is irrelevant to discussion of what happens beyond the Chandrasekhar limit. 2 years after Chandrasekhar did his work in 1930, the subatomic particle, the neutron, had been discovered. And less than 2 years after that, Walter Baade and Fritz Zwicky first proposed the existence of the neutron star. The discovery of the neutron had led to the understanding that the nucleus of an atom consisted of protons and neutrons with a cloud of electrons around the nucleus. The proton has a positive charge, the electron has an equal negative charge, and the neutron, which is slightly heavier than the proton, has no charge. What Baade and Zwicky theorized was that under sufficient pressures, the electrons would combine with the protons via a process called electron capture to produce more neutrons. These neutrons would then be subject to the same quantum snobbery of the Pauli exclusion principle that prevented electrons from getting too close in white dwarfs to produce a neutron degeneracy pressure that, in combination with other nuclear forces, would provide another stable point resisting gravitational collapse. This model also helps to explain supernovas, not the kind that I described in my last video of self-destructing white dwarfs, but the kind that results from the death of a star of more than 10 solar masses. When stars that large run out of fuel, their core can't be supported by the white dwarf process and undergoes a catastrophic collapse, generating neutrons that will lead to the formation of the neutron star, but the outer layers get heated up in the collapse and there is a massive fusion flash that blows the rest of the star away in a supernova. This was all fascinating, but partly due to Franz Zwicky's difficult personality, plus the fact it was thought these objects would be undetectable, meant that they remained unverified theoretical curiosities for several decades. However, in 1967, Franco Pacini worked out that they might emit radio waves, and at the same time, Jocelyn Bell and Anthony Hewish picked up odd signals from their radio telescope in Cambridge. This regular series of pulses, each 1.3 seconds apart, was utterly unlike anything that had been detected from space previously. In fact, the regularity of it was so unusual it almost looked like an artificial beacon, and the signal was initially given the semi-joking name of LGM1 for Little Green Men. But it was quickly determined that it was a natural source, that of a rotating neutron star. Anthony Hewish was later awarded the Nobel Prize for his discovery. His co-discoverer Jocelyn Bell was not. That's another Nobel Prize controversy that I'm not going to get into here. So what are neutron stars like? Well, due to the different way they're formed, the smallest neutron star can actually be slightly lighter than the heaviest white dwarf, and they range between 1.1 to 2.1 solar masses. But the neutrons can be packed much more closely together than the material in a white dwarf. So whereas a white dwarf might be about the size of the Earth, a neutron star is perhaps just 10 kilometers across, vastly denser. So if we use our reference object of a cherry tomato, which again, if it was made of white dwarf material, would weigh about as much as an African elephant, if this was made of neutron star material, then it would weigh somewhere within the ballpark of Uluru. That hugely concentrated mass makes everything about neutron stars ridiculously extreme. For example, they have magnetic fields that are anywhere from hundreds of millions to a quadrillion times stronger than that of the Earth. And those magnetic fields generate beams of radio waves that are emitted along the north and south magnetic poles. Similarly to Earth, the magnetic poles do not necessarily align with the rotational pole, meaning that as the neutron star spins, this beam of radio waves sweeps across the heavens like a cosmic lighthouse. And that's what Jocelyn Bell and Anthony Hewish discovered, this beam of radio waves sweeping across the Earth in a regular series of pulses that gave the phenomenon its common name of pulsar. But for them to be detecting a pulse every 1.3 seconds means that's how fast this object heavier than the Sun is rotating. And that's because as it's collapsing down in the supernova that gives birth to it, all of that mass is being pulled in and it spins faster, similarly to how an ice skater spins faster when they pull their arms in. And 1.3 seconds sounds fast, but it's far from the quickest. There are some what they call millisecond pulsars, and the fastest spins on its axis 716 times a second, while weighing more than the Sun. That extraordinary density also leads to massive surface gravity. Now I'll go into more detail about that in my third video on black holes, but suffice to say that a neutron star can have a surface gravity 200 billion times stronger than that of the Earth. If you dropped a 1 kilogram weight 1 meter above the surface of a neutron star, it would hit travelling at 1400 kilometers per second with an explosive force equaling 200 tons of TNT. That gravity is so strong that it bends light, such that if you're looking at a neutron star, some of the light rays being emitted from the far side will be curved around and you will see more than 50% of its surface. You will see some of the far side because of the bending of the light waves. They are some of the deadliest objects in the universe. They emit huge amounts of ionizing radiation that would sterilize anything that got close to them. In the unlikely event you were able to shield yourself from that, the magnetic field would interfere with the biochemistry in your body and kill you that way instead. And yet, despite this hostility, it's possible for neutron stars to have planets, presumably having either survived the supernova or be captured later. In fact, the very first planets that were discovered outside the solar system were found orbiting a pulsar back in the early 90s, and they were discovered because as they orbit around the pulsar, they alter the timing of those pulses very slightly. Even accounting for small discrepancies like that, the timing of signals from pulsars is so reliably regular that it has been suggested they be used as a sort of galactic GPS, capable of locating things with a high degree of accuracy across interplanetary or even interstellar distances. In fact, several space probes that were launched by NASA back in the 70s, Pioneers 10 and 11 and Voyager 1 and 2, had plaques with messages on them in case they got picked up by aliens at some point in the distant future, including a pulsar map indicating the planet of origin of the probes. I wouldn't be worried about visitors. It's going to take hundreds of thousands of years for those probes to get anywhere close to another star. Now, for years it was thought that neutron stars were the last stop before oblivion, that there's no other mechanisms like electron or neutron degeneracy that could prevent larger, more massive objects from collapsing into black holes. But there are hypotheses. One such is quark stars. Now, protons and neutrons are not themselves fundamental objects. They are in turn made up of even smaller particles called quarks. And under ordinary circumstances, it's literally impossible to rip a quark free from a proton or neutron. It takes so much energy to do so that by Einstein's E=mc² equation, that energy can create mass of new quarks that will immediately bind to the one you tried to rip free. But perhaps in neutron stars massive enough to just be teetering on the brink, it's possible that the core may contain free quarks. There have been conjectured observations of quark stars before, but several of them have turned out to be false alarms. But there is one candidate discovered in the last couple of years that is still being investigated and may possibly be one of these quark stars, even more extreme than neutron stars. So there we go. That is a tour of some of the most extreme objects in the universe, and I am very glad that the closest one to our solar system is over 400 light years away. So in my third and final video, I will talk about the most mysterious objects in the universe, black holes. I'll try and debunk one or two myths about them. See you then.